Hello, 4th grade. I hope that you all had a wonderful Easter break. Today we're going to be getting back into our unit on simple machines. And what I'm going to do is I'm going to review a little bit about the lever, which we learned about last time, and then introduce two more simple machines for us to add to our list right now. So first off, let's review what a simple machine is. And I said, very simply, that simple machines are devices that help us apply force. And I gave a list of all the simple machines that we talked about as well. Lever, pulley, inclined plane, wedge, wheel and axle, and screw. And a lever is what we talked about last time. So in a lever, basically we have this lever arm, so this like a plank or it's almost like a seesaw sort of shape. And there's a pivot point where everything turns on this one point, so that's like the middle of the seesaw, and that is the fulcrum. And basically what we do is if we want to lift a load on one side of the lever, we put effort down onto the other. So we apply a force, we push on it, or pull on it, depending. We push our pull on one end, and that moves the other end. So if I push down here, whoops, if I push down, it'll push the load up. So that's the motion of the lever here. And we also talked about how we can move the fulcrum to give us a mechanical advantage when moving the load. So if we move the fulcrum toward the effort, that gives us a shorter lever arm that we're pushing on, but it moves the load a lot farther. So notice how we're not moving as much on the side that we're pushing on, but the load is moving pretty far. And I used a big arrow to represent this because it takes a lot of effort or a lot of force because we have shortened the distance that we have to push. So we have to push harder over a shorter distance. Likewise, we could also move the fulcrum towards the load, so we have a very long lever arm that we're pushing on. And in that case, notice how far the arrow is moving, how far the effort side has to move, how far we get to push, and how little the load actually moves. So the load moves just a little bit, but we're pushing quite a long ways. And because that work is spread out along a longer distance, it's going to be a less force required to get the same work done. So that's why there's a small arrow here with the longer lever arm, because it gives us a certain mechanical advantage there. So just to give you a summary of how the lever works, and these are the key points for you to take away with the lever, is that when you have a longer lever arm, you don't have to push as hard, but you have to push for a farther distance. So if you have a really long lever or a handle on something, it makes it easier to push, but you have to push it farther in order to get the same work done. And a shorter lever arm, you need more force, but it is less distance required. So you need to push harder, but you don't go as far. And if you remember, we had a scientific definition of work, and that was force times distance. So how hard you're pushing something times how far you're pushing it. So in order to do the same work, that explains this longer and shorter lever arm. So if we were doing the same amount of work with a longer arm as with a shorter arm, with a longer arm, we have more distance, so you just don't push it as hard in order for the force times distance to balance out. With a shorter arm, because you have less distance, you have to push it harder in order to balance out. You have to make up for the work that you, for the short distance, for the distance that you don't have. So a classic way to think about this, and I don't think I went into a lot of detail on this last time, is a seesaw or a teeter-totter at the playground. And I have a nice little image here. You can actually effectively play on a seesaw with somebody who's much larger or much smaller than you just by changing the length of the lever arm. So I don't know if you've ever noticed this, and if you get a chance, I highly encourage you to do it because it's a lot of fun. If you find somebody that well, let's just say someone that's the exact same weight as you, and you sit on opposite sides of the seesaw. What's going to happen is if you're sitting exactly the same distance from the fulcrum, you're going to balance out. You can kind of both be floating in the air. But then if one of you scoots closer, like say you scoot closer to the middle, you have a smaller lever arm then, and your force is still the same. Your weight is still the same pushing down. So if you scoot closer to the middle, all of a sudden the other person pushes you up. But if you scoot towards the back, all of a sudden you have a longer lever arm, So you have a mechanical advantage, and you push them up. So if you have someone that's much heavier than you, I could seesaw with somebody that's 3 times my weight. All I have to do is sit very far back on the seesaw, and they have to sit very far forward, and then our lever arms and our weight balance out so that we can actually push each other up and down. So have fun experimenting with that if you ever get a chance to play on a playground with a seesaw. Also, and this is another at-home example that you can all try, is you can experiment with a door. A door is actually a type of lever, believe it or not. It's a different type of lever, so the fulcrum isn't in the middle of the lever. The fulcrum is actually right on the very end of the lever arm. So there's kind of like the hinge and then the door coming out. And this is the fulcrum. The hinge is the fulcrum, and then the whole door moves along that hinge. And so what you can do to experiment with lever arms is have a door maybe sitting halfway open, and I want you to try pushing it open really close to the hinge. So not like in that crack, 'cause I don't want you to like smash your finger in the door, but like try pushing right next to where the hinge is on the door, and you realize you have to push really, really hard in order to move the door. So go ahead and give that a shot. Even today, I think that'd be a fun experiment for you to do. And then try pushing at different places on the door and see which places are easier to push and which places are harder to push. And you'll notice that where it's harder to push, you actually aren't pushing quite as far. So if you're pushing right next to the hinge, you're only pushing a couple inches total, but you have to push really hard in that distance. And if you're pushing where the doorknob is, you have to push it that whole length, the whole swing of the door, but you don't have to push it very hard. So a fun experiment to try at home, and it'll help you to think through how lever arms work. But for now, we are going to go into a couple other simple machines. So here's our list of all the simple machines that we have, and we already talked about the lever. And today we're going to talk about 2, and they're things that you might not even think of as machines, but they do fit into the category of simple machines because they help us apply force. And they are the 2 triangle-looking ones, the inclined plane and the wedge. So let's go ahead and talk about these guys. Now, I'm going to move my window over here. I want you to imagine for a minute that I'm asking you to climb to the top of the Eiffel Tower. And let's first off imagine that you are climbing just straight up. So you're right at the bottom of the Eiffel Tower. You're not using stairs, you're not using an elevator, none of that. None of those cheating ways of getting to the top. You're going to climb up using your arms. I want you to think about how difficult that would be to climb up the Eiffel Tower, going straight up. So you can imagine this is you down at the bottom, and this is the Eiffel Tower, not drawn to scale. And you end up climbing all the way up to the top using your arms, and you end up at the top. You'll get up to the top, you'll be very, very tired and exhausted, and probably not have enough energy to come back down, and you'll be stuck up there for a long time until somebody comes and gets you, I guess. Or you take the elevator down. Now, I'm going to imagine that same scenario where I'm asking you to climb to the top of the Eiffel Tower, but this time you have stairs, a nice long staircase that goes up. Again, it would still be tiring to go to the top, but it probably won't be quite as tiring as it would be to climb up using your arms, like just climbing straight up the Eiffel Tower. This one, it kind of spreads it out a little bit. You have all these steps that you have to go up to get to the top, but you're not going straight up. So each step, yeah, sure, it takes a bit of energy, but it doesn't take quite as much effort as it does when you are going straight up. Now, third example, let's say that instead of going straight up or having a normal staircase, you actually have a ramp. So let's say we build a ramp that's like a mile long going up to the Eiffel Tower. And you just walk along that ramp. You'll notice that walking along this ramp, it actually feels quite easy. You just walk right along, and it's just like you're kind of walking along a sidewalk. Like you're not going, it's not too steep, it's actually a pretty flat ramp overall. You just kind of feel like you're walking forward. And then at the end of it, oh, look, I'm at the top of the Eiffel Tower. Isn't that great? And to my knowledge, there is not such a ramp going to the top of the Eiffel Tower. But if there were, this is what it would be like. It would be pretty easy to walk up. I mean, it would be a very, very long ramp, maybe even miles long. But it would be a nice, easy walk. You wouldn't feel like you're going straight up. Now, this is how an inclined plane works. So an inclined plane is the simple machine we're talking about next. And it is a plane on an incline. So if you think of a plane is kind of like a surface and an incline means it's slanted. So an inclined plane is a slanted surface. So it's basically a ramp. So when you think inclined plane, think ramp. And here's a picture of a guy using an inclined plane to push a wheelbarrow of dirt or something into what looks like a barn. So what an inclined plane does is it basically makes it so you can move things up and down in more efficient ways, in ways that make it feel like you're not going straight up or straight down. So if this guy were to try and lift this wheelbarrow straight up, like say he was standing next to this doorway that he's trying to get into, and if you just try and lift the wheelbarrow up and put it up there, that'd be a lot of effort, a lot of force required. But what an inclined plane does is it spreads out that up and down distance over a long way. So it changes the force times distance. It increases the distance so that it requires less force. So when he has a nice ramp, it doesn't feel like he's just pushing the wheelbarrow straight up. He just pushes it forward, and it kind of goes up on its own as he pushes it. So let's see here. Hang on, sorry. There we go. Okay. So the way an inclined plane works is it spreads out the work of moving up, which makes it easier. So I have here kind of a diagram of two roads. Like imagine two bike paths, and they're both climbing up the same hill. Both bikes are starting at the bottom of the hill, and they climb up to the top. The blue arrow represents how far up they move, and the black lines are the ramps that they use to get up that hill, so kind of the path. A steeper path, so a steeper inclined plane, will get the bike up to the top of the hill faster. So the bike on the left has a shorter distance to go to get up to the top. But the bike on the right has a more flat surface to ride on. So it's going to be easier for the bike on the right to pedal and make headway than the bike on the left. I mean, that's a very steep ramp, and I don't know if you ever tried biking up hills. It's not always the easiest thing to do. And the steeper the hill, the harder it is. And that's because you're moving more straight up and down rather than just left and right and forward. Here, the bike on the right is moving more flatly, so he moves a longer distance, but it makes it feel like he's not moving up as quickly. So it feels easier to move up. The bike on the left is moving up more quickly, so it feels harder for him. And that is the way an inclined plane works. It's a ramp. Now, the other simple machine we're going to talk about is a wedge. Now, a wedge basically lets you change a forward force into a sideways force. And I'll give you a diagram here in a moment. And it's often used for splitting things. So I have a nice little diagram of a guy splitting wood. And I was looking for one that used an axe, because axes are cool. But he's not using an axe, he's using something else. But it has a wedge on the end of it. So an axe is a wedge, and this yellow device that the guy is using is also a wedge. Basically what it is, it looks like a triangle, and you poke it down into something, and as you push it in, it splits that thing apart. Again, it's not something we normally think of as a machine, just like we don't think of a ramp as a machine, but it is a very, very useful tool that helps us apply force in efficient ways. So if any of you get the chance to split wood one day, I encourage you to do it. It's a fun exercise, and makes you feel manly. But okay, so here's how it works. You have your wedge, so we can say that's the axe head going into the wood, and we're pushing down into the wood. And what happens is, notice how it's a nice little triangle here. The point of the triangle can go in pretty easily. And as you push down, and that's what's labeled the input force in this diagram, as you push down that wedge into the wood, the triangle gets deeper and deeper in, and actually kind of pushes the wood apart. So you see this output force here going in either direction. You push down, and it actually pushes the wood out to the side. And that's how you end up splitting it apart. So wood actually splits very nicely when you use a nice sharp axe. So just to show you that little video again, you can see how it works. He works it in, and it starts to split, and as he goes farther and farther down, the triangle part of the wedge pushes it farther and farther apart until it actually just splits right open. So that is how a wedge works. Now, here's a couple other examples of a wedge that you might use perhaps even on a daily basis. One is a knife. So a knife is a very, very thin wedge. If you look right at the edge of a knife, you can actually see it has a nice little triangle shape right at the end. That triangle shape is the wedge. So what happens is when you're cutting your carrots, making a soup, you put the edge of your knife into the carrot, and that very, very thin piece of metal can get in very easily, and then as you push down, the triangle kind of starts to go in, and it pushes the carrot into 2 pieces, and then you have cut your carrot successfully. A nail is also an example of a wedge. Notice how at the very end of the nail you have a little point. That is the little triangle that can go very easily into wood, and as you hammer that nail into the wood, it actually forces its way in, and it kind of opens up a little hole for the rest of the nail to go in. And then it's nice and tight in there. It's very much wedged into the wood, and that's why nails can hold wood very well, because they've wedged themselves in. So that is all that I have for this lesson right now. As I've encouraged you to do before, keep your eye out for simple machines around you. So think about lever arms you might be using anytime you're pulling on a handle, or using a seesaw, or whatever. Or look for inclined planes. Whenever you're using ramp or stairs, it's sort of like an inclined plane. Keep your eyes out for wedges and knives and axes and all that good stuff. So just keep your eyes out for simple machines, and you'll be amazed at how many there are around you every single day. Until next time, take care.